Hello and welcome to this BioProcess International Ask the Expert webcast. I'm your host, Leah Razan, the online editor for BioProcess International. Before we get started, just a couple of notes. This webcast is being recorded and will be made available for replay in the multimedia section of our website. We've muted the audio lines, but we welcome you to type in your questions for our speaker in the chat window on your screen. After the presentation, we will begin the question and answer portion, and I will ask our speaker your questions from the chat window. Your questions in the chat window will only be visible to myself and our speaker. So thank you for joining us today. It is now my pleasure to introduce our speaker, Xuemei from Bio-Rad Laboratories.
Welcome everyone. Today we're going to talk about a new mixed mode chromatography resin, Nuvia aPrime 4A. This is a hydrophobic anion exchanger, and we can take a look at the structure of the ligand. It has a positive charge in a hydrophobic moiety for engaging the biomolecules via electrostatic interaction or hydrophobic interaction during separation. So the base particles of this resin are polymeric polymers with open structures, open pore, and this will allow the efficient mass transfer of the biomolecules in and out the pores during the separation. And we also engineer these particles to make them mechanically strong. So during large-scale bioprocessing, they are going to offer good pressure flow properties. Depending on the PI of the target protein, the Nuvia aPrime 4A chromatography can be run in either the flow-through mode or bind in elute mode, depending on the interaction between the target molecules and the ligand. And as we know in all chromatography separation methods, the buffer pH and conductivity will impact the charge and hydrophobic interactions between the ligand and the molecules, and we can improve the selectivity and recovery of the target by variation of buffer compositions. So let's first take a look at the purification of a basic protein. The goal for this purification is to remove product aggregates. And as we know, the PI of the proteins is at 8.45. It's pretty basic. So at neutral pH, it's going to carry a positive charge, and the electrostatic repulsion between the molecule and the resin's ligand, we expect that the target molecule is going to be in the flow-through fraction, and we use this Nuvia aPrime 4A column to retain other unwanted impurities. So DOE was used in the initial condition screening, as we know that the feed will come in with around 100 millimolar sodium chloride. So we look at the effect of buffer pH on the purity of the target monomer content in the flow-through fraction. You can see here there's not much variation if we perform the flow-through operation at pH 6.5 versus 7.5. On the other hand, operation at pH 6.5 is going to give us a lot better recovery of the monomer in the flow-through fractions. We scale up the purification with a packed column. As you see here, we load equivalent to 3-column volume of conditioned feed on a column that's equilibrated with 20 millimolar sodium phosphate, 100 millimolar sodium chloride at pH 6.5. We were able to recover the target molecule within 5-column volume with a recovery of target monomer at 94% and reduced the monomer reduced the other impurities in the process, like whole cell proteins and DNA, from 150 ppm down to 4 ppm for HCP, and then the DNA from the whole cell proteins were not detectable. And during this process, we were able to recover the monomer at over 99%. And I would want to point out the shape of the flow-through fraction here. You see there's no toweling as the outcome of our open pore structures of the particles, and probably also suggests there is no non-specific interaction between the target molecules and the resin. For acidic protein purification, Here I'm showing a case of a IgG4 monoclonal antibody with a PI of 6.9. This monoclonal antibody was initiated, purified, captured from control cell harvest at neutral pH. However, when we performed the elution at acidic pH from protein A, we saw a lot of dimer and tetramer formation during pH 3 elution. That indicates that this map is not that stable under acidic condition. So we would like to use Nuvia aPrime chromatography to do additional polishing purification to remove those product-related impurities. So again, we use DOE screening to see how under what condition the MAP-S was bound. And you can see here the DOE result with a wide range of pH. We were able to bind the MAP-S efficiently in the presence of up to 100 millimolar of sodium chloride. We did similar DOE screening for the elution condition, and knowing the MAP-S is not stable under strong acidic condition, we stay away and try to recover the MAP-S monomer at mild acidic pH. With a large column, we were able to determine the dynamic binding capacity of MAP-S. At 300 centimeters per hour, we were able to achieve over 50 milligram per mil binding capacity at 10% breakthrough. And the bound MAP-S monomer was recovered with an elution buffer at pH 6, and we saw that this fraction basically contained only the MAP-S monomer, and all the other unwanted dimer and tetramer will stay on the column until we strip the column with pH 4 buffer. We compare the purification performance of MAP-S with two other hydrophobic anion exchangers, capital A here and capital A here in press. The major difference is at the elution at pH 6, we did not see MAP-S monomer eluted under this condition, and all this monomer together with the dimer and tetramer are staying on the column until it was stripped at pH 4. So this result suggests that the binding of MAP-S by capital A here is stronger, and there's no resolution of monomer from dimers or tetramers under the identical condition. So we suggest that if you have a new molecule, you want to develop a process for its purification, screening multiple resins is recommended because you are going to understand more about the interaction and come up with the best process. Besides playing with buffer pH and conductivity, we can also use additive in the Nuvia aPrime chromatography for a different kind of selectivity between the target molecule and impurities. We know that the glycine, this amino acid residue, actually enhances hydrophobic interaction between proteins and hydrophobic chromatography stationary phase. And it is a switcher ion with minimum effect on buffer conductivity. So we don't expect the charge interaction between target protein molecule and the resin will be affected. And moreover, we know that glycine has been used to stabilize protein during chromatography. So now let's take a look at the separation of two acidic proteins with similar or essentially the same PIs, human serum albumin and the soybean trypsin inhibitor. So we attempt to separate these two proteins on a classical anion exchange chromatography resin, and we were not able to separate them. However, if we equilibrate Nuvia aPrime 4A column with a buffer at neutral pH with 100 millimolar glycine, we were able to bind both test proteins on the column. And if we apply a gradient between buffer A and buffer B, that is a acidic buffer at pH 4.5 without glycine. We saw there is a peak at the end of the gradient, and the gel electrophoresis show that this is the human serum albumin. So what's going on is during the gradient, we drop the pH of the buffer from 7.5 to 4.5, and we also eliminate the glycine in the buffer. This acidic pH buffer actually neutralize the surface negative charge on HSA, and at the same time, with the removal of the glycine, we reduce the hydrophobic interaction between HSA and the resin and achieve the elution. On the other hand, the other test protein, STI, is staying on the column until we elute it with a low pH buffer with a high concentration of sodium chloride. So now you see they are well separated, and it's easy to convert the gradient elution into a step elution that we first eluted the HSA with low salt, and then elute the STI with a buffer containing 1 molar sodium chloride. From this separation, we can tell that the Nuvia aPrime4A has a different selectivity compared to the traditional anion exchangers, because it is able to differentiate the minor hydrophobicity difference between these two test proteins and achieve a nice separation with sharp peaks and baseline separation. So for large-scale production, we will need to have larger column. So we started the packing of Nuvia aPrime4A in a 20 by 20 column, checking the pressure flow properties. As you can see here, the packing quality is pretty good, and we were able to achieve 300 centimeters per hour without hitting high pressure. You see here we are well below 2 bars at 300 centimeters per hour. And the dynamic binding capacity of human IgG was not affected at 150 centimeters per hour up to 250 centimeters per hour, showing that the large pores of these particles actually would still allow the efficient interaction between the resin and the target molecules without being affected by flow rate. And for large-scale production, we would like to see a packed column would be able to handle multiple yield cycles without compromising the purification performance. And here we test the packed column stability with a polyclonal human IgG, and we were able to repeat the purification cycles for up to 200 times without seeing the drop of binding capacity or target recovery. So to summarize the presentation today, I hope I have shown you the data on the Nuvia aPrime4A. This hydrophobic anion exchangers can effectively separate targets from impurities because we optimize the ligand density and hydrophobicity. And most of the time, the separation can be performed under gentle conditions with excellent target recovery. The purification can be operated in both flow-through or bind and elute mode, and it can be further improved by the use of buffer additive. Overall, the method development is straightforward, and we show you data that how to use the column for large-scale process production. And the product is offered in multiple formats. Like you see here, we have the 96 well plate, up to 5 mil 4-size column for your condition screening and method development. And for large-scale production, we also offer bulk resins. For additional information like user manual or application notes, you can go to our website at Bio-Rad.com. You can request samples there too. You can contact our process specialists for additional technical support, and we are often on the site to help you if needed. With that, I'm happy to answer all the questions you may have. Thank you.
Okay, great. Thanks, Xuemei. So the first question that we have is, have you packed any columns for process production?
Yes. As you have seen in the presentation that I show you the data with a 20 by 20 centimeter column, it was done in an in-place column by axial compression. We also test packing in other column hardware, for example, the BBG columns at 10 by 20, 14 by 20, 20 by 20. We studied the effect of the compression factor, packing solutions, slurry percentage, axial compression versus flow pack, and the stability of the column during the use cycles you saw in the presentation. But if you need assistance in packing large column, you can contact us and we will have a field support specialist. They are going to be on your site and help you pack if needed.
Okay, and is it simple to develop a process with a resin that has multiple modes of interaction?
Yes. I think the process development is still pretty straightforward, as you have seen many cases I presented today. That we always begin with DOE to screen the conditions and then come up with the initial methods. Then we pack a larger column for further optimization. So this is essentially the same strategy we've been using for the traditional IEX or hydrophobic interaction chromatography. And in case you need to use additive, you simply just put them in your DOE table and screen like other buffer components. If you want to get input from us in your DOE design, or you want us to help in data interpretation, you can feel free to contact us and we'll be happy to assist you too.
Are there other additives that you've studied, and what are their effects?
So besides the glycine we show you today, we also study, for example, arginine, and we found that in general, arginine helps reduce non-specific interaction and improve elution efficiency. And there are other additives like propylene glycol, glycine. In general, they modulate the hydrophobic or electrostatic interactions. So you can use this additive to change the binding capacity, selectivity, and resolution. Urea and guanidine hydrochloride, we also tested and we found they are most useful in column cleaning and regeneration.
Okay, and it looks like we have time for one more question. If we didn't get to your question, we'll pass it on to Xuemei and she'll be able to follow up with you directly. So again, if you have other questions, go ahead and type them in and we will pass those on to Xuemei. But the last question we're going to ask here is, what's the difference of Nuvia, aPrime 4A, and other hydrophobic anion exchangers like Capto adhere?
This is an interesting question. So we have been comparing the physical and chemical properties of these resins and how these properties impact the chromatography performance. So physically, we know that the Nuvia aPrime particles have larger pore size. So you've seen today that usually a Nuvia aPrime column gives you a sharp flow-through or elution peak due to the efficient mass transfer of protein molecules. And you also saw that the MAP-S was bound much stronger by the Capto adheres. So we believe there is difference in the interaction between the ligand and the protein molecules between these resins. We will continue our investigation and sure we will share with you our new results in future presentations and publications. So please stay tuned.
Okay, great. Thanks, Xuemei.
Thank you.
And thank you to our audience for joining us. The recorded version of this webcast will be made available for on-demand viewing on our website, and as a registered attendee, you'll receive a follow-up email providing you with a direct link. We look forward to having you join us at future BioProcess International Ask the Expert webcasts. Look for those announcements in your inbox. Goodbye.